Our project is Machine Comprehension with BERT for Group 29, and our advisor is Professor Dana. Background, so we're trying to create a QA system to answer contextual questions based on an article. So given this article on private schools, our model should be able to answer these questions. So for example, along with sport and art, what is the type of talent scholarship? And the answer is academic. So our model should be able to give these answers to these questions. So the existing solutions are Microsoft's machine reading comprehension, which uses unidirectional language models, not bidirectional, and BiDAF, which is also a bidirectional attention flow model, but it fails to capture long-term dependencies. So our proposed solution is machine comprehension with BERT, which is a bidirectional encoder to help the accuracy.
When it comes to our scope of work, we decided to split our project up into 5 phases to easily manage it. The first phase was actually creating the Q&A system with BERT, and then we moved on to phase 2 to improve this architecture with Albert using embeddings and additional layers. Our phase 3 instantiated a backend API, which we created and deployed. Phase 4, we created and deployed the front-end application itself. And phase 5 is tentative, something we're working on is actually using the knowledge base of the internet. When it comes to our progress, the way we split it up was basically one half was phase 1 and 2, and the other is phase 3 and 4. So for phase 1, we worked with the Squad 2.0 dataset. This is the Stanford question and answer dataset. We had single models, we had base layers, frozen layers, downstream layers, and different hyperparameters when we were tuning our model. For the application itself, we worked with Angular 9.0 on the front end, and this was hosted on an AWS S3 bucket. The backend API hosted the actual model itself and sent JSON objects, and this was on a Heroku server. The core features of our website was to have a paragraph which was served as the context and have a question, and it would predict the answer of the question using the context of the paragraph you submitted.
So Albert, released in 2019, is an enhanced version of BERT that focuses on using hidden layer embeddings to learn context-dependent representations. So to increase the model size without running into GPU limitations, Albert employs 2 parameter reduction techniques. Factorization of the embedding parameterization decomposes a large vocabulary matrix into 2 matrices. Thus, the embedding parameters are reduced from big O of V times H to big O of V times E plus E times H, where V is the vocabulary size, H is the hidden layer size, and E is the embedding size. So this is a significant reduction as the vocabulary size is significantly less than the hidden layer size, and so is the embedding size. It's also less than the hidden layer size. And cross-layer parameter sharing shares all the parameters across all the layers and prevents parameters from growing with the depth of the network. So for our machine comprehension model, we ran a variety of experiments to determine the optimal model. And the base layers for our models involve either BERT or Albert. Drawing inspiration from computer vision models, we played around with freezing different base layers, such as the embedding and encoder layers. And to adapt BERT and Albert for machine comprehension, we needed to add some downstream layers to calculate the scores for the start index and the end index of the answer sequence. So the configuration for these layers include adding 1 fully connecting layer, adding 2 fully connecting layers, and adding convolutional layers. And the constants for these experiments, as for the hyperparameters, include a max sequence length of 512, 2 epochs, a batch size of 4, and a learning rate of 10 to the negative 5. And these hyperparameters were shown to be optimal in other experiments with respect to our limited compute capability. So if you look at this this table, you can see that the parameters of Albert are significantly less than BERT with the same layer sizes and hidden layer sizes. So this makes training much faster and easier. And to rate the performance of our models, we utilize the dev set of Squad 2.0, which is an extension of Squad 1.1 with unanswerable questions. So thus Squad 2.0 is a much harder data set for machine comprehension, and the measurements are exact match and F1 score. And as you can see, our model significantly outperforms BiDAF and Microsoft MRC by almost 5 percentage points in exact match, and it's a much more rigorous data set with Squad 2.0. And more importantly, our model is a single model, non-ensemble model, so it requires much less compute resources for inference. In this table, we summarize the most promising experimental results. The baseline of comparison for these models is the BERT model with no frozen base layers and one fully connected linear downstream layer with 768 input features and 2 output features, which correspond to the scores for the start index and the end index of the answer sequence. When we freeze up parameters in the embedding layers, the performance was slightly improved with a noticeable improvement in questions with answers. This result is promising since it can help us lower the training time with fewer gradients to compute. As for adding another linear layer, our tests indicate no performance gains. For the convolution layers, we experimented with different configurations, but it turns out the simplest model achieved the best results with an exact match score of 76.70 and an F1 score of 79.89.
Moving on to the demo, we will illustrate our model compared to Microsoft MRC, which uses ReasonNet, and the BiDAF model. So to begin, we're going to be using an article on Tesla, and our first question will be, who is the co-founder of Andreessen Horowitz? So to begin, once I press submit, our model will come up with an answer. Our model correctly answered. So ReasonNet has a similar layout. So we have the context here, the question, we get our answer. ReasonNet also answers the question correctly, Mark Andreessen. And finally, moving on to BiDAF, we'll ask the same question with the same context. BiDAF incorrectly answers the question and gives us an answer of German automaker Volkswagen. Shows a situation where our model is superior to BiDAF. Moving on to the second question, we will ask, what is the most valuable auto company? After pressing submit, we correctly get the answer of Toyota, which is indeed the largest auto company. Moving on to MRC, we ask again, what is the largest auto company? The answer once again is Toyota, and then we ask, what is the most valuable auto company again? For BiDAF, we also correctly get the answers Toyota. This is a situation where all three models correctly get the answer. Moving on to our third scenario, we will ask, who is the CEO of Tesla? And interesting about this question is that the answer is not located within the context. So our correct answer should be CLS, which means there is no answer. After pressing submit, our model gives us the correct answer of CLS, meaning the answer isn't included in the article. Asking the same question to Microsoft MRC, they give us the answer of Mark Andreessen. The reason MRC is wrong is because it always tries to give you an answer, even when the answer could not be in the context. This also holds true for BiDAF, as if we ask who is the CEO of Tesla, they will also try to give you an answer, and here they would give us mid-January.